Welcome, engineers. My name is Travis IQ, and today we're discussing the OSI model. We're more likely discussing some components of the OSI model, right? We had a video earlier in the week discussing the layers of the OSI model, the Open Systems Interconnect model. Today I'd like to discuss some components associated with the layers in the OSI model. So if we recall, the layers of the OSI model, layer 1, the physical layer, is what we're looking at here. We have specific components of the network architecture that live at layer 1. You would say components of the network architecture that live at layer 1. What components of the network architecture live at layer 1? I would say cabling, right? So what we actually have down here is cabling labels and a couple of devices, any devices that convert signal types. So if you're going from like optical signal conversion, or if you're going from optical to copper, these types of things. So signal converters, right? Those are all layer 1. They're changing layer 1 signal types, right? Our hub is basically just a multi-port repeater. And a repeater is a device that simply repeats signal. It does nothing with the signal. It doesn't look at any header information, which makes a whole lot of sense because there are no headers at layer 1. And so you would say, Travis, I don't feel like I see a whole lot of hubs in my environment very often, if you are more familiar with networking equipment, right? And I would agree with you. I would say that there is one specific time where you would see a hub in use, and that would be in network sniffing applications. A little 3-port hub would be very useful if I wanted to take signal in one interface, repeat it out, every component of that signal, right? Every packet on that wire, and then take the 3rd port and plug in my host. So here's an example of a time where you would use a layer 1 device, I suppose, right? Layer 1. Oh, our cabling standards, right? Cat 5 and Cat 6 cable. We'll talk a little bit more about cabling standards, but all these termination types as well, T568A, T568B, RJ45 registered jack, right? Connector types and things like patch panels, keystone jacks, any of these connector types. Those would all be physical specs. They're important to us, don't get me wrong, right? Physical connections are very important. If you ever tried to connect a monitor to a PC and you had only RS-232 and your new PC only had DVI and HDMI interfaces, right? That's a physical cabling problem that really affects how these things get wired together. If all you had were RJ45 jacks and you were trying to connect a high throughput optical interconnect, right? Then you're going to have a problem because you only have copper interfaces and you need an optical terminal, right? That being said, these are some components that live at the physical layer. Let us move on. How about layer 2? What lives at layer 2, Travis? Switches. Switches live at layer 2. These are also known as multi-port bridges. The term bridge would be pretty useful to you because we still use it in the networking world sometimes. If you think about a protocol like spanning tree, we'll talk about spanning tree at another time, but spanning tree, for example, uses the term root bridge. Really what we're talking about is a switch there, right? It's just a multi-port bridge. Why do we say switches, let's say, live at layer 2, right? Why do we say that? Because what a switch does is a switch looks at layer 2 header information. Layer 2 header info. Right? And in our traditional Ethernet environment, right, a layer 2 header would be an Ethernet header using MAC addressing. So switches look at MAC addresses, and make forwarding decisions. And you would say, okay, Travis, so they look at MAC addresses and make forwarding decisions. How does a switch look at a MAC address and make a forwarding decision? How does a switch, right, look at a MAC address inbound on of a frame inbound on an interface and make a forwarding decision? Well, how do we make any decisions, right? Usually in the computing world is the table of values. And this would be something like a MAC address table. That's absolutely right. We'll go in and take a look at MAC address tables and traditional switching functionality in a simulated environment at some point, right? But for now, that's how switches make these forwarding decisions. A MAC address table, or a CAM table, would be another term for this. Content addressable memory. And so in this list of tabulated values, right, I have MAC addresses associated with these interfaces. And I have a port associated with that MAC address. Gigabit interface G00, for example. And so when I see this MAC address as a destination MAC coming into this port, I forward it out the appropriate port that it is destined for. How do I generate this table as a switch? Switches generate this table by looking at MAC addresses, lo and behold, right? How would you determine which MAC address is associated with which interface? You would look at where it came from, right? So I can look at source MAC and log the source MAC. And then I log the source MAC address associated with that interface and put it in my table, right? So who's transmitting on this interface? I log it, put it in a CAM table, and then I can look that MAC address up when it's a destination MAC. This is what we mean by, if you ever heard the term switches live at layer 2, right? Or switches operate at layer 2. That's what we mean by this, right? And these here are examples of Cisco Catalyst switches. And this here is that standard switch image. Okay, what hardware lives at layer 3? The network layer. Routers. What information lives at layer 3? IP addressing. So routers live at layer 3, and routers make forwarding decisions based upon IP address information, right? So if routers are looking at IP addressing information, right, then they have a table of IP addressing info, a route table. This is how we make decisions, tabulated values. And in this case, we have IP addresses or networks. And we'll talk about 32-bit addressing structures and IP addressing structures and network information and subnet masks and things like this. But let's save that for a later date. So I have a route statement, right, that says the 192.168.1.0 network lives out the fast Ethernet 00 interface. We could have some other information associated here, things like metric information or hop count or those types of things to make routing decisions. We could have information about how that route was learned, right? A lot of information contained here. But regardless of the information type that's contained in the table, the router still has to make a forwarding decision and decide where to send the traffic. This is our standard router image. And this is a router in a sample network rack. This is actually my rack, by the way. Well, one of my sample racks. Routers live at layer 3. There may be one other component that you might think lives at layer 3, and that would be a layer 3 switch. Now, Travis, doesn't a layer 3 switch operate at layer 3? You are absolutely correct. Right? A layer 3 switch is a big multi-port device, like a switch tends to be, right, that makes forwarding decisions based upon both layer 2 and layer 3 information. This will make our lives easier by integrating layer 2 and layer 3 functionality into one component. And again, there are benefits and drawbacks to these types of things. And one of the big problems that you have when you start integrating components, right? So why don't we just do layer 2, layer 3 functionality and some additional functionality that we'll talk about at the upper layers, right? Why don't we do that in just one big hardware component? And the answer is we can't pack enough computing power, computational power, RAM, storage, all this stuff. We can't pack enough information into one device to do all those things for a 10,000 node network. Right? So we have to break this hardware out. And that's why we have different components that operate based solely upon one layer of the OSI model, one set of header information. Okay, Travis, then what devices live at layer 4? Layer 4 is the transport layer. Remember we said layer 4 is TCP and UDP protocols. And we can talk more about the protocol operation, right? But TCP, for example, is connection oriented. Right? So we can have we have hardware utilities like firewalls. This would be a Cisco's ASA and adaptive security appliance. This is what our physical device looks like. This is how it's represented in network diagrams traditionally, right? A brick wall, a firewall. And if this firewall, if this traffic filtration device, right, we're looking at TCP information. What is some traditional TCP information? Port number? How about information associated with the TCP header? Things like TCP flags and logging TCP flags. Things like synchronization flags, acknowledgement flags. Looking for something like a three-way handshake. What I'm describing to you is a specific firewall type. It's known as a stateful firewall. We can delve a little bit deeper into firewall types in a more in-depth firewall discussion. But if I were looking at TCP flags and keeping a table of which devices, which hosts on my network have established connections with remote hosts, that would be known as a state table. State table. And I can look up the state of the link. What's a valid link state? Established, for example. And if that link has been established, then what I will do is allow that packet. Because a connection has already been established from an internal host to that external host. And I should then allow that traffic. This would be an example of layer 4 functionality. And finally, if you remember, we said we should group layers 5, 6, and 7 basically together as application layer information. If I had a piece of hardware, a firewall, for example, content filtering, firewall, right? Then I have a firewall that's looking at application layer information, right? It's looking for information that's stored in applications. What are some application information storage formats? XML, the extensible markup language, JSON, JavaScript, object notation, HTML, hypertext markup language, right? These are all information formats, right? Or application formats that I can look for and filter out. And you would say, Travis, could you give me some specific examples of XML or JSON filtration? I would say let's keep that for a later date. We have gone all the way up the stack, describing hardware associated with layer 1, layer 2, layer 3, layer 4, and 5, 6, and 7. I would say this discussion is sufficient for this video, but we will continue to elaborate on this, as always, in later videos. As always, engineer, break stuff, and have fun.